Okay, so let's start. So I'd like to thank Ludmil for his place in the front of the room this morning. The morning session, we'll start the morning session. So it's a great pleasure to introduce Donu Arapura, who will. Hello?
I don't hear you.
Anyway, I just wanted to say it's a great pleasure to introduce Donu Arapura, who will speak on Torelli action on representation varieties.
Okay. All right. So thanks. Can everyone hear me? Because I can't tell, but let me know.
It's good.
Okay. Great. Thanks. Yeah. So I'm actually. Thanks for everyone for the invitation. I wish I was there. But unfortunately, I'm in India right now, so it's this is actually the best way. But yeah, so so you have the title, and this is actually joint work with Dick Hain, and it's sort of a preliminary work, but I think it's stable enough to announce a few results. So let me just start by just fixing some obvious notation. So G is going to be genus, and it's going to be at least 2. In some cases, 3 is better. And let's sigma be a compact-oriented topological surface of genus G. So I haven't fixed a complex structure yet. And pi or pi G, if I want to specify G, is just the fundamental group, which has a standard presentation, which I think everyone knows. I didn't write it down. All right, so that's just a notation which I'm going to keep for the rest of the talk, which I assume it's an hour talk, but I only prepared an hour, so yeah. So yeah. Okay. All right, so let me again, just laziness. G is going to be SUN. In theory, it could be some other compactly grouped, but mostly in this talk, SUN. All right, so that's just notation. Now let me introduce some of the main players. So this is the representation variety. So it's sort of a fancy R. And if I want to specify the rank, I'll write Rn, but usually N is fixed. And it's just this set of homomorphisms from pi, which is the fundamental group of the genus G surface, into G. And it's a set, but it actually has a structure of a real algebraic variety. And G acts on this set by conjugation. And I just take the quotient, and this is sometimes called a character variety. So if you think in terms of what the objects are, the points of this would represent conjugacy classes of representations. And so, as I said, these are real algebraic varieties. All right, so the mapping class group, was that a question? Or, yeah, okay. So the mapping class group I'll just write as gamma, or again, gamma G, and there's a couple of different incarnations depending on your taste. You can take so sigma, let's say it's a C infinity surface. So it's orientation preserving diffeomorphisms. That's a huge group, but just take the connected components pi naught, and that'll give you a discrete group. Or from a more algebraic geometric point of view, it's if you take the moduli space of curves, it's the orbifold fundamental group. All right, so there's usual problems which I'm not going to, which I'm going to ignore, which I think everyone knows. Right. So, yeah. So, so pi acts on R or R mod G by gamma acts on pi. So, therefore, it acts on these associated varieties R and RG. All right, so I'm most interested in the cohomology of these things. So, yeah. So again, the mapping class group, which is called gamma, acts on the fundamental group of sigma, And I usually think of this as a rational vector space. So if I forget to specify coefficients, it's Q. And this has a more structure than a vector space. It has an intersection pairing, which everyone knows. And the mapping class group action preserves that. And so I guess I just contradicted myself. So maybe I should think of this as integral cohomology for the next part. So gamma, which is the mapping class group, will map to the symplectic group, and it's actually an onto map. And the kernel is by definition the Torelli group, which is the main player for this talk. It's written as TG, or if G is fixed, just T. So, and that's a somewhat mysterious group, which one would like to understand. And so the starting point for this talk was a result of Cappell, Lee, and Miller from about 23 years ago. I'll explain exactly what they stated, but there's a slight generalization due to us. And for any n, which hopefully I said n is at least 2 here. The action of TG on the degree 6 cohomology of this character variety is non-trivial. Okay, so that's result. And what actually, yeah, okay. I jumped a slide here. So what actually Cappell et al. Dealt with was the SU2 case. And so I guess we can do the higher rank case, but we really just reduced to their work. So it's in some sense the SU2 case is the main case. All right, so let me say a few words about how the proof goes. I mean, not in any detail, but just a very rough idea. So we use the same strategy as these 3 authors. And there's a slight, I guess we can claim we have some slight simplifications or modifications to their argument. So maybe I should have reminded you, but I don't want to jump back on the slide. So R was the representation variety. So this was the set, which is a real algebraic variety of homomorphisms of pi, which is the fundamental group of the genus G surface, into G, and G acts on that. So you can consider equivariant cohomology, which, if you're not familiar, it's defined on the right of this equation. So basically, it's morally the cohomology of the quotient if the quotient was nice. And unfortunately, it may not be nice. So there's a standard trick you do, which is to sort of stabilize it by crossing it with a universal G bundle, which lives over which is usually written as EG, and that lives over EG. And then G will act diagonally on this product, and you just take the quotient that way. So morally, it's not any different than the quotient, but it has better properties. So this is the so-called homotopic quotient or Borel quotient, and the usual cohomology of that is by definition this equivariant cohomology. All right, so that's just notation, but now let me get into more serious structure. So there are certain universal Chern classes in this equivariant cohomology of C cross R, and I should point out that G acts trivially on the C factor. And maybe this slide is a little cramped, but sorry about that. Was there a question or? Yeah, go ahead.
What is the curve? The curve means sigma. sigma.
Oh, yeah. Sorry. Yes. So sigma was yeah. C is for curve, but sigma is for surface, I guess. But yeah, sigma. That's sigma. Thank you. Any other questions? Or okay. Yeah. So I apologize. My Zoom skills have atrophied over the last year. I've been giving actual talks, and except for just now. All right. So yeah. So anyway, so Atiyah Bott in their famous paper on Yang-Mills on Riemann surfaces, they analyze the structure. Well, they don't directly do this, but their results imply this. They analyze the structure of this equivariant cohomology, and they find that it's freely generated by the Kunith components of these universal clauses. And the notation is a little bit ugly. I apologize, but the only one we have to keep track of for later is I marked in red. It's CJ hat, and then these other ones are the other factors. All right, so so what does freely generated mean? Well, it's an exterior algebra on the odd factors and a symmetric algebra on the even degree factors. That's what I mean. All right, so so maybe, as I said, the equivariant cohomology of R is morally the cohomology of the quotient, and in fact there is a map from the cohomology of the true quotient to this equivariant cohomology. Unfortunately, or maybe fortunately in our case, it's not an isomorphism in general, but it is an isomorphism over the locus parametrizing irreducible representations, which I write RS because S stands for stable. I guess that may not show up in the arguments in the slides, but it does show up in certain arguments. Okay, so let me see. I don't know if I'm going too fast or not, but if I'm rushing, just slow me down. All right, so I'm trying to give you some outline of this theorem, and I'm just sort of introducing a little bit of the structure to this. Okay. So the point of that theorem is to prove that the action of the Torelli group on this degree 6 cohomology, not of the equivariant cohomology, but of the true cohomology of the quotient, is non-trivial. Okay, I messed up. So yeah, there's no way to compile this while giving a talk, or at least it would be a big mistake. So if you can mentally change that should be the actual cohomology of R2 mod G. Sorry about that. Yeah, so there's a certain polynomial which I prefer not to write, but it's not very complicated. But it's a polynomial in these terms which I alluded to in the previous slide, C2 hat, etc. Okay. Yeah, sorry. This lives in equivariant cohomology of R2, and it lifts to a class in the true cohomology. And TG will act on this non-trivially. All right, so
R2 mod G, it lives to a class.
R2 mod G, yes, thank you. Yeah, okay, that was definitely a typo. So R2, if you can mentally change that to a mod G, that's what it should be. Okay, so maybe this is more detailed than you want, but when I say non-trivial, you can actually say a little bit more about what in what sense it's non-trivial. So if you take the lift of this class and look at it as a G module, then it fits into this extension, which is somewhat fundamental in this story. And Dick is, I think, in the audience, so you can ask him about this. This is related to stuff he knows well. But it's a non-split extension. That's the key point. So, and that's where the non-triviality comes from. Right. So maybe I squeezed too much into this slide, but I'll just finish it. So this is the rank 2 case up to this point, and then basically we can do the rank n case by just considering the map induced by symmetric powers. I mean, again, there's some small calculations to handle, but you can show that the non-triviality in rank 2 gives you the same result in rank n. All right, so that's the first theorem, which is all right. So I'm going to switch from topology to more algebraic geometry. So up to this point, I've been working with completely topological objects. Now, so somebody asked me what C is, and C is now correct. It's a choice of a smooth projective curve of genus G. So topologically, it's sigma, but it's sigma plus a complex structure. All right. So again, I'm going to throw in some notation. So there's sort of a fancy looking M, N, or MNC if I want to specify C. This is the moduli space of semi-stable bundles, whose definition maybe I should have recalled, but I didn't write it down, of rank n and degree 0. So maybe I can say it without trying to write it, since I don't have any way to write it. So with semi-stability, if you look at a subbundle of your given bundle, let's say it's E, we're already saying it's degree 0, so any subbundle has degree less than or equal to 0. That's the semi-stability condition. So with one exception, which actually we can ignore just by choosing these numbers large enough, this is actually a singular projective variety. And the singularity will actually be important for what I'm going to do. So in fact, let's assume that one or both of these numbers is at least 3. All right, so let me just recall an old theorem of Narasimha and Sheshadri. So the previous space that I was talking about, R mod G, and this space in algebraic geometry, M and C, are actually homeomorphic. So this is a complex algebraic variety. This is a real algebraic variety. So you can say a little bit more. They're actually equivalent as real algebraic varieties. And so I'll just say in passing that if you choose a complex structure on sigma, that imposes 1. You can read this as saying that imposes 1 on the character variety. And again, I didn't write this down, but maybe I can say it. If I give you a representation of G, I just take the associated flat bundle, and one checks that that is in fact an object here. And that's what the map is. You just take the representation, send it to the flat bundle, and that's it. All right, so let's get into some Hodge theory, since I think that's one of the themes of the conference. So of course, by Deligne, we have a mixed Hodge structure on the left. And since these are homeomorphic spaces, their cohomology is the same. And because the left side or the space on the left is singular, let's say in most cases, it's really a mixed Hodge structure. And by deleting the weights are between 0 and j. Okay. So I want to emphasize that the mixed Hodge structure is very much dependent on C, and that actually will show up implicitly, at least on some of the arguments. Okay, so I think hopefully going at a reasonable pace, but again, you should slow me down if you want to ask questions. So yeah, so this is a little bit vague, but I think you hopefully get what I'm saying. So if I let C vary in the moduli space of curves, the cohomology on the top will move, and in a precise sense, it'll give you an admissible in the sense of Steenbrink and Zucker, Kashiwara, a variation of mixed Hodge structure. And if you don't know what admissible, it just means it's a really nice variation of mixed Hodge structures. And the point that links this part of the talk with the previous part is that the monodromy action is the previous action of the mapping class group. Right, so I'm being again maybe a little bit cavalier in the orbifold story, but I think it's probably okay for this audience. You have to be a little careful about what you mean here, but this is only the orbifold fundamental group, but in a reasonable way, this is a correct statement. All right, so what am I trying to say? So yeah, all right. So maybe this is really a special case of something that I'm going to talk about in a bit, but this is really what I was trying to get to, that if C is very general in moduli space, this mixed Hodge structure is genuinely mixed. What I mean by that, it's not a direct sum of pure Hodge structures. I mean, it's really something. And let me give you a sketch, and I think probably for this audience, these words make sense, so I can just say it. So what I said in the previous half of the talk, well, maybe not half, third of the talk, is that the monodromy action, well, maybe I didn't say it exactly, but I implied it, that the monodromy action, which is the previous mapping class group action, is not semi-simple. And you can relate that to the generic Mumford-Tate group, and that would imply that this is not reductive. And if it were pure, it would have to be reductive. Pure and polarized would have to be reductive by standard stuff in the story. So that means it's mixed. All right, so in case you were wondering what the topological import, what the Hodge theoretic import of all of that is, this is where it's heading. All right, so let me say a little more about the previous statement. We can actually refine that a little bit. So I said that there's these universal Chern clauses. Maybe I should just, I don't know if it's a good idea to give you too much notation. This stuff is notational. I think I just skipped it. Yeah, so there's universal Chern clauses in this product, and use the Kunis decomposition and take one of the factors, and it's this guy here. And right. So maybe it's okay to, here it is. Yeah, so these are the ones that showed up earlier in the talk. But now we have a map from the cohomology of this moduli space to the equivariant cohomology. And again, since we're moving into more algebraic geometry, one way to interpret it, if you prefer this, is that this is a map from the moduli stack, or sorry, the moduli space to the moduli stack. So this homotopy quotient construction is really picking up the cohomology of the moduli stack, which is actually in a simpler has a simpler structure by a T above. So the thing on the left is actually the more mysterious cohomology. All right, so there's a natural question here. So this fellow lives on the right. We have a map from here to here. Can I lift this class to the cohomology of the moduli space? It's a natural question, I hope. And the answer is no. In fact, no in a very low degree. C2 hat does not lift to H4. All right, so yeah, so one, this was not our intention, but it just sort of fell out of what we were doing. There's an old theorem of Ramanan that there's no Poincare bundle on this moduli space, and I should emphasize or remind you that this is degree 0, which is sort of the bad case, but for us it's actually the interesting case. And in this case, there's no Poincare bundle. It's not a fine moduli space, and so we found this gives you a Hodge theoretic proof of that, and the proof is just basically one line. Suppose there was a Poincare bundle, then the Kunith component of its second Chern class would give you a lift, and we just said there is no lift. So yeah, that's
Yeah, I mean, it should be
sorry.
bundle and C.
Sorry.
And C.
Richard time.
I'm sorry.
There's a question.
Yeah, it was.
I'll handle something. Yeah, I mean, it should be no Poincare bundle on C cross MN.
So sorry. Yeah. So C cross, yeah. Yeah. So right. Yeah. C. Yeah. I wish I could live tech this thing, but I think I shouldn't take a risk. Yeah. There should be a C cross, and yeah, that's right. Yeah. Anyway, maybe if you want the slides later, I can just fix these typos as I go. All right. So, yeah. All right. So, although CJ hat won't lift, there is a sense in which there are universal Chern classes, and I think this is actually kind of an interesting story. And I think I can jump into the statement right now. So as I said, the cohomology, now I got the C cross MN here. So this carries a mixed Hodge structure. And because the cohomology, the space whose cohomology we're taking is projective, it's going to have weights from 0 to 2J in this degree. So this is the top weight quotient of this mixed Hodge structure. So it's a pure Hodge structure actually of weight 2J. So and I guess I should have said this, but I mean I should have written this, but I'll say it. In fact, for each J there is a Hodge class, because we have a pure Hodge structure. We can talk about Hodge classes, CJ tilde, which is universal in the following sense, namely, if I have a family E of semistable vector bundles of rank n in degree 0, then I get sort of a classifying map from the parameter space, sort of the base of that family to here, and I can pull back these classes, these tilde classes, and then that will pull back to the Chern class CJ. So in that sense, these are universal. Right, so yeah. So yeah, so this is maybe this last furthermore will make more sense if I had said these classes are actually Hodge classes. So you can ask whether, I mean, the map from, again, you have to imagine, I'm doing this on a blackboard, the map from the cohomology of H2J to this quotient is surjective, right? So I can, of course, lift this to the cohomology of H2J. There's no content to that. But can you lift it to a Hodge class? And the answer is no. In fact, it fails for C2 tilde. So so that in some sense complements with the previous statements. All right, so yeah, so let me say a word or two about the proof. So I have a feeling I'm going a little bit too fast because I'm going to run out of slides. I generated 49 slides and I'm already on 42. So I can go say this really slowly. So there's a standard trick in this business. If I take E, so I'm being abusing notation a little bit. I'm thinking of a point in here as an actual bundle on C. And it's a bundle of degree 0, but here I can use a standard trick. I can twist the bundle by some ample class, sufficiently ample class, and regard Mn is instead of degree 0, degree very high degree, so suitably high degree, still rank N. And I can make the degree so high that these bundles, all of them, not just one, are globally generated. And moreover, this the dimension of the space of global sections is some universal polynomial in the rank and the genus. It's just, so all I'm saying is that the first cohomology vanishes and then you throw it into Riemann-Roch. So it's whatever you get from Riemann-Roch. So yeah, so that's just a technical point, but the technical point is used in the next item. So let's Q be, so I'm actually going a little bit into the construction of this moduli space, which is standard, but maybe it's good to recall it. So Q is the quote scheme of parametrizing these bundles with a fixed basis. Right, so it's not just bundles, but bundles. So if you like, they're based bundles. And this quote scheme is represents a functor, so it is a fine moduli space. But of course, you've added extra data to this moduli space to recover Mn. You have to quotient out by what you've added, which is sort of a change of basis. So you take the GIT quotient of Q by GLNC acting by change of basis, right? And that's the standard construction. I mean, there's variants of this, but I guess this is maybe Carlos Simpson's version of this. I guess the original version is due to Seshadri in the 60s. All right, so yeah, so Q was this quote scheme. So I'm trying to go slow because there's a lot of notation now. I think I went too fast. And now Kerwin applies to any GIT situation. So I apply it to this one. And what she says is that you can form sort of an equivariant blow-up Q naught of Q, which is nice. So maybe I didn't say all the words. What does nice mean? It means that it's going to be a sequence of blowups with G equivariant smooth centers, and the quotient M naught, the GIT quotient, is Orby smooth, by which I mean it has only a finite quotient singularity. So it's a rational homology manifold. So it's in some sense it's as good as smooth. And moreover, the map induced on the quotients from M naught to M is birational. So Kerwin calls this a partial resolution because there may be mild singularities, but you can just view it as a very nice resolution in this situation. So maybe I should explain where this is going. So there's this mixed Hodge structure, and if you recall, or if you've ever been through Deline's construction, you build a mixed Hodge structure by the cohomology of a hypercover. So I'm actually going to look at the first few steps of the hypercover, but I'm going to choose the hypercover so that it's compatible with the GIT nature of this construction. All right, so M naught is the first stage in this hypercover, and fortunately, I don't think I need to tell you what the next stage is. But in case you want to do it, you would take the basically fiber product of M naught cross M naught over M, and then apply Kerwin again, and that's M1. And you keep going if you want to build a whole hypercover. All right. So here I'm going to be a little bit vague, but basically using Deline's recipe that from Hodge 3 and Kerwin, you'll find that this top quotient is in fact the image of the cohomology of C cross M into the cohomology of C cross M naught. Okay. So that gives you a sort of a nice handle on this piece of the mixed Hodge structure. All right, so as I said, maybe a previous slide, that Q is representing some kind of functor, and it's the functor that classifies based vector bundles of the appropriate type. So there's a universal based bundle, we'll call it E, or script E. All right, so now I can tell you what these universal classes are, the CJ tilde, and they're the jth equivariant Chern class of the pullback of, maybe I'm saying too much in one sentence, of E to Q naught. So maybe I just remind you, Q naught was this blow up. On the first space, we have this E, script E. I pull it back to Q naught. G, or rather GLN, is acting on everything in sight, and this map is equivariant. And so you can form some equivariant version of Chern class, and that's what CJ tilde is. All right, so in a nutshell, that is it, except you have to maybe stare at this isomorphism to convince yourself that whatever this equivariant fellow is, it lives here in some sense. One has to prove that it actually lies in the image of this map. Thereby, via this isomorphism, it actually lies in this quotient of this top weight graded quotient of the mixed Hodge structure. So I didn't write it, but that's the idea. Right, so that's how you prove the first half of the theorem. It's actually more than the first half. It's maybe the first 90% of the theorem. So that's where these classes come from. There is something to check to prove that it's universal, but maybe it's a little technical and not so appealing for a talk. And then there's a last bit which I should explain briefly, the furthermore. Yeah, and that was this non-liftability, and this follows from the earlier results, basically from the first half of the talk. And that's apparently all I have to say. So, do you want to hear it again? Yeah. Okay. So that's actually my talk. So, do you have questions or comments?
Hi, thank you, Donu, for a very good talk.
Okay.
Okay, so are there any questions?
Hi, this is Daniel Litt. So in the beginning of the talk, you produced kind of the extension corresponding to the Johnson homomorphism in cohomology.
Oh yeah. So let me jump back to that. It was like early on in the story.
So I was wondering, is there like a geometric way to see that should appear in H6 of the character variety?
So I'm sorry if you could say it a little bit. It's somehow there's an echo.
I was wondering, is there like a geometric way to see that extension should appear in the cohomology of character variety?
Yeah, so it does show up in the cohomology of the character variety. Maybe let me interpret your question as does it have a geometric meaning? In this case, we believe so, but I think we haven't completely sorted out what it should correspond to in the character variety or the moduli space. But I suspect it's closely related to these universal Chern classes. So maybe that's another step that needs to be added to round out this picture. I don't know if that's answering anything. Just a vague comment.
Other questions? Yeah. I have a question too. For one thing, at some point we went from H6 to H4. How did that happen?
I'm sorry, what?
At some point we went from H6 to H4.
Oh yeah, right. So maybe I should have written out this guy here. So yeah, so maybe yeah, it would have made more sense if I wrote the formula. So I'll just say it. So V is going to involve C2 hat. I actually don't remember off the top of my head, but it's up to some coefficients. It's C2 hat times P2 plus or minus the sum of these phi classes from the previous slide. Yeah, here. So it's a polynomial in these classes here. There's a C2 hat. There's some of these and there's some of these, and so V lives in H6, but in some sense the constituents of V come from H4 of the product. So they're basically coming from the second Chern. I mean, they're basically Kunneth factors of the second Chern class of the universal bundle. That's roughly the point. So yeah, so I guess it is a bit confusing. So H6, at some point I'm switching from H6 to H4, but H4 of the product of C cross the moduli space.
Okay, my other question, what can you say for moduli and bundles of degree D instead of degree 0? For example, is it first, if D is copond to R, does this phenomenon not happen at all? And
yeah, exactly. I should have said that. So in the case where D and N or the rank are coprime, none of these phenomena occur. In other words, this Torelli, so maybe here's the third. So in this case, so if I changed, well, I should change this to M of degree D rank R, where D and N are coprime, then this action is trivial. In fact, in other words, all, not just in degree 6, but in all degrees, the cohomology will basically factor through the symplectic group. And not just the cohomology as a representation, but as a motive. It's basically coming from the curve. So in some sense, our interest is.
What about, are there intermediate cases where, D is non-zero, but has shares of common factors with the rank?
Yeah, that's a good question. So if it's if N and D have common factors, I would expect there's a similar phenomenon. But honestly, we haven't got that far in the story to say for sure. But I'm assuming that we're going to see the similar kind of story, maybe not in degree 6, but in some other degrees. Yeah, but in the case of coprime, none of this happens. Yeah.
Any other further questions?
So in degree other than 6, the original paper of Cappell, Lee, and Miller, they have a non-trivial action of TG, right?
Oh, yeah.
Do you expect to explain that?
Yeah. So again, it's really, I mean, I guess I can just be, yeah, it's kind of embarrassing. So it's still at a preliminary stage where we were focusing on degree 6, mainly because that's the case we can handle. But I expect it's true for a whole range of degrees. And certainly Cappell, Lee, Miller, they don't just do a degree 6, they actually do a whole range of degrees. In fact, they tell you exactly what degrees, in what degrees it's non-trivial. And it would be nice to have a similar result in rank N. We haven't got there yet, but that's really something on the horizon which we hope to do. Yeah, so 6 is really just hopefully a temporary thing. It's just the first case we can get our hands on. I mean, basically the formulas start to get really messy, and in degree 6 you can sort of do it, and then after that I just put stuff on a computer, and I got polynomials of degree 30, and I eventually gave up. So yeah, it's really just laziness.